About approximations and errors. General concepts of approximations and errors. 1. Approximation. A value that is close but not exact to another value. 2. Error. The difference between an approximation and the exact value. 3. Absolute error. The magnitude of the difference between an approximation and the exact value. 4. Relative error. The ratio of the absolute error to the exact value, often expressed as a percentage. 5. Accuracy. How close an approximation is to the exact value. 6. Precision. How close multiple approximations are to each other. 7. Systematic error. An error that consistently occurs in the same direction. 8. Random error. An error that varies unpredictably. 9. Truncation error. The error that occurs when a number is rounded or truncated. 10. Round-off error. The error that occurs when a number is rounded. Approximations in mathematics. 11. Linear approximation. Approximating a function near a point using its tangent line. 12. Taylor series approximation. Approximating a function using a series of polynomials. 13. Numerical integration. Approximating the definite integral of a function using numerical methods. 14. Numerical differentiation. Approximating the derivative of a function using numerical methods. 15. Interpolation. Approximating a function between known data points. 16. Extrapolation. Approximating a function beyond the range of known data points. 17. Least squares approximation. Finding the best fit line or curve to a set of data points. Approximations in science and engineering. 18. Experimental error. Errors that occur in scientific experiments due to factors like measurement uncertainty, equipment limitations, and human error. 19. Modeling error. Errors that occur when a mathematical model is used to represent a real-world phenomenon. 20. Simulation error. Errors that occur in simulations due to factors like discretization, numerical methods, and assumptions. 21. Engineering tolerance. The allowable variation in a manufactured product or component. 22. Statistical inference. Making inferences about a population based on a sample, which involves approximation and error. 23. Monte Carlo simulation. Using random numbers to simulate a probabilistic process, which involves approximation and error. Error analysis and propagation. 24. Error propagation. How errors in input values affect the error in the output of a calculation. 25. Maximum absolute error. The largest possible absolute error in a calculation. 26. Maximum relative error. The largest possible relative error in a calculation. 27. Error analysis. The process of identifying and quantifying errors in a calculation or measurement. 28. Sensitivity analysis. The study of how changes in input variables affect the output of a model. Specific approximation techniques. 29. Euler's method. A numerical method for solving differential equations. 30. Runge-Kutta methods. A family of numerical methods for solving differential equations. 31. Simpson's rule. A numerical method for approximating definite integrals. 32. Trapezoidal rule. A numerical method for approximating definite integrals. 33. Newton's method. A numerical method for finding roots of equations. 34. Secant method. A numerical method for finding roots of equations. 35. Bisection method. A numerical method for finding roots of equations. Applications of approximations. 36. Physics. Approximations are used in many areas of physics, such as classical mechanics, quantum mechanics, and thermodynamics. 37. Engineering. Approximations are used in engineering design, analysis, and simulation. 38. Computer science. Approximations are used in algorithms, data structures, and numerical methods. 39. Statistics. Approximations are used in statistical inference, hypothesis testing, and confidence intervals. 40. Economics. Approximations are used in economic modeling and forecasting. Error reduction techniques. 41. Improved measurement techniques. Using more accurate instruments and methods to reduce measurement errors. 42. Better experimental design. Designing experiments to minimize systematic and random errors. 43. More precise calculations. Using more accurate algorithms and numerical methods. 44. Error correction. Using techniques to identify and correct errors in data. 45. Calibration. Ensuring that instruments are properly calibrated to provide accurate measurements. Common errors and pitfalls. 46. Assuming exactness. Assuming that all measurements and calculations are exact. 47. Ignoring significant figures. Not paying attention to the number of significant figures in calculations. 48. Misusing units. Using incorrect or inconsistent units. 49. Overfitting. Fitting a model too closely to the data, leading to overestimation of accuracy. 50. Underfitting. Fitting a model too loosely to the data, leading to underestimation of accuracy. Historical context of approximations and errors. 51. Ancient civilizations. Early approximations and error analysis can be traced back to ancient civilizations like the Babylonians and Egyptians. 52. Greek mathematicians. Greek mathematicians like Archimedes and Euclid developed methods for approximating geometric quantities. 53. Medieval astronomers. Medieval astronomers used approximations to predict astronomical events. 54. Scientific revolution. The development of calculus and other mathematical tools led to new methods for approximation and error analysis. 55. Industrial revolution. The need for accurate measurements and calculations in manufacturing led to advancements in approximation techniques. Modern applications of approximations and errors. 56. Artificial intelligence. Approximations are used in machine learning algorithms, neural networks, and deep learning. 57. Data science. Approximations are used in data analysis, data mining, and data visualization. 58. Climate modeling. Approximations are used in climate models to simulate the Earth's climate system. 59. Medical research. Approximations are used in medical research to analyze data and develop models. 60. Financial modeling. Approximations are used in financial modeling to assess risk and make investment decisions. Philosophical implications of approximations and errors. 61. Nature of reality. The concept of approximation raises questions about the nature of reality and whether it can be perfectly understood. 62. Limits of human knowledge. Approximations highlight the limits of human knowledge and the difficulty of achieving absolute certainty. 63. Role of uncertainty. The concept of error emphasizes the importance of uncertainty in scientific inquiry and decision-making. 64. Epistemology. Approximations and errors are relevant to epistemology, the study of knowledge and its limits. 65. Ethics. The concept of error raises ethical questions about the consequences of making mistakes and the importance of accuracy in various fields. Mathematical tools for approximations and errors. 66. Calculus. Calculus provides the foundation for many approximation techniques, such as Taylor series and numerical integration. 67. Linear algebra. Linear algebra is used to analyze errors and solve systems of equations. 68. Statistics. Statistical methods are used to analyze data, estimate parameters, and quantify uncertainty. 69. Numerical analysis. Numerical analysis provides techniques for approximating solutions to mathematical problems. 70. Computer programming. Computer programming is used to implement approximation algorithms and perform error analysis. Specific approximation techniques, continued. 71. Romberg integration. A numerical method for approximating definite integrals. 72. Gaussian quadrature. A numerical method for approximating definite integrals. 73. Richardson extrapolation. A technique for improving the accuracy of numerical approximations. 74. Chebyshev polynomials. Polynomials that are used for approximation and interpolation. 75. Lagrange interpolation. A method for interpolating a function between known data points. Applications of approximations and errors, continued. 76. Aerospace engineering. Approximations are used in aerospace engineering to design and analyze aircraft and spacecraft. 77. Civil engineering. Approximations are used in civil engineering to design and analyze structures, such as bridges and buildings. 78. Environmental science. Approximations are used in environmental science to model and analyze ecosystems. 79. Materials science. Approximations are used in materials science to study the properties of materials. 80. Psychology. Approximations are used in psychology to analyze data and develop models of human behavior. Error reduction techniques. Continued. 81. Data cleaning. Removing errors and inconsistencies from data. 82. Data validation. Checking data for accuracy and completeness. 83. Robust statistical methods. Using statistical methods that are less sensitive to outliers and errors. 84. Cross-validation. Evaluating the performance of a model on a separate dataset. 85. Bootstrapping. A statistical technique for estimating the uncertainty of a model. Common errors and pitfalls. Continued. 86. Ignoring correlation. Failing to consider the correlation between variables in a model. 87. Assuming linearity. Assuming that relationships between variables are linear. 88. Extrapolating beyond the data. Extrapolating predictions beyond the range of the data. 89. Confusing correlation with causation. Assuming that a correlation between two variables implies causation. 90. Misinterpreting p-values. Misinterpreting p-values as measures of the 100 facts about approximations and errors. Continued. Common errors and pitfalls. Continued. 91. Misinterpreting p-values. Misinterpreting p-values as measures of the strength of an effect. 92. Overlooking confounding variables. Failing to consider confounding variables that might influence the relationship between two variables. 93. Using inappropriate statistical tests. Using the wrong statistical test for a given data analysis problem. 94. Ignoring measurement error. Failing to account for measurement error in data analysis. 95. Assuming normality. Assuming that data follows a normal distribution without checking. Mathematical tools for approximations and errors. Continued. 96. Probability theory. Probability theory is used to quantify uncertainty and analyze random errors. 97. Differential equations. Differential equations are used to model many real-world phenomena and can involve approximation techniques. 98. Optimization. Optimization techniques are used to find the best approximation or solution to a problem. 99. Computational geometry. Computational geometry is used to approximate geometric shapes and solve geometric problems. 100. Symbolic computation. Symbolic computation is used to perform algebraic manipulations and simplify expressions, which can be helpful in approximation and error analysis.